Okay, so welcome to the afternoon session. This session is supported by TNQ Publications. And the first speaker is Professor S.R.S. Varadhan from Courant Institute, New York University. He will speak about large deviations of a tech particle. Professor Varadhan.
Thank you. I want to thank the organizers for inviting me. I visited Pune and ASEP maybe 10 years ago. It was just beginning to develop, but I see now it's fully developed, and it's a pleasure to come back here again. I'm sorry about the date. I know it's January 2nd, but I had it prepared yesterday, so the date is automatically put down. So I'm going to talk about large deviations of a tag particle. And this is joint work with Chandrasekharan of the University of Arizona. We consider nearest neighbor simple exclusion process in one dimension. This is like single lane traffic. You can't overtake anybody. You can't bump into anybody. So there are particles that are located at at some of the integer sites on Z, which is set of real integers, one dimension. And you can have at most one particle per site. So there are empty sites and occupied sites. Each particle waits for an exponential random time of mean 1, and then attempts to jump one step either to the left or to the right. The probability of choosing to jump right is P, and the probability for choosing to jump left is Q, which is 1 minus P. Of course, if the site is empty, the jump is successful. But if the site is not empty, then it cannot jump and gives up the chance to jump and waits for another exponential random time. So that's how the process develops. Notice in this process, the number of particles is conserved. So you're not either creating or destroying particles, they're just moving around. So the state of the system can be described by a function eta, which is defined for every point on Z, and eta x equal to 1 means there is a particle at the point x, at site x, and if it's 0, that means there is no particle. So eta x is 1 or 0, depending on the site being occupied or empty. So this whole process can be described by a Markov process, and you can write down the generator of the Markov process. If you take the generator of Markov process is described by what? By an operator, and the operator describes all possible transitions that can happen in the process. So here you see that it's P times eta times 1 minus eta. Eta times 1 minus eta tells you that there is a particle at eta and an empty site at x plus 1. If that's the case, there's a probability P that you can jump. Or you can have a jump the other side with probability Q if the site to the left is empty. So one of these things, all these possibilities are happening simultaneously. So you have a whole system of particles moving around randomly from time to time. This evolution has a family of translation invariant stationary measures. They are Bernoulli product measures, piece of rho, where every site is occupied with probability rho and free with probability 1 minus rho. And different sites are independent, so it's a product measure with density rho. And we condition to have a particle at 0 and tag it. So because of independence, the distribution at other sites is Bernoulli. And we denote by xt the position of the tagged particle at time t. So the whole thing is moving and we are tracking the tagged particle. Now the case when p equals 1 is special. The particle only wants to jump to the right, never to the left. That's referred to in the literature as TASEP, a totally asymmetric simple exclusion process. We generally assume P is greater than Q, so preference is moving to the right. And if it's not the extreme case, P is not 0 or 1, that's called simply asymmetric simple exclusion process. We're interested in the large deviation properties of 1 over n x of n t. We start initially with x0 having the initial distribution with Bernoulli measure P rho. So you start initially with the invariant distribution, but condition that at 0 there is a particle. The law of large numbers will tell us the particle moves asymptotically with speed 1 minus rho times p minus q. That's natural. 1 minus rho is the probability of finding an empty site. Once you have the empty site, you have probability p for the right and q for the left. So the expectation of the size of the jump is p minus q. So it's natural that the expectation is this. But the question is, do you actually have law of large numbers? It's not difficult to prove because the distribution seen from the tagged particle is still Bernoulli product measure. And so that comes easily. Now, it's made easy in some sense for the TASEP because one knows the exact distribution of xt. It's known, for example, xt is a Poisson distribution with mean t times 1 minus rho. That's only for TASEP. So in particular, one knows that the probability that x of n t is equal to k is given by the Poisson probability. And this means you can compute directly that x n t over n converges to the mean of the Poisson random variable, which is t times 1 minus rho. And then you can compute the large deviation probabilities too, because you want to compute the probability x n t over n is close to at, and you know exactly what the probabilities are. So you can take the probability, take log, divide by n, and see what happens asymptotically, and you get a formula for it, which is very explicit, which is just the exponential rate of decay of a tail of a Poisson distribution. Now, the one question one can ask, okay, I've seen this large deviation with this tagged particle moving very far, but initial condition caused it. Well, there are two possible reasons why the tagged particle can go fast. One, maybe the initial condition was such that there's some empty free space, so it could move freely at a rate than what it normally would in a crowded environment. Or it could be it's speeded up, but speeding up requires space to speed up. Maybe it was just a combination of having space and speeding up, or maybe just having space. There are various possibilities. You could have a large deviation. There are three regions that handle differently. Let's pick the time to be t equals 1. Then the particle might have moved a distance larger than 1, or a distance between 1 and 1 minus rho, or a distance which is a which is less than 1 minus rho. And these are likely to have different origins. If a is bigger than 1, 1 is the natural maximum speed of the particles. So the particle has to, even in empty space, it would travel with speed 1. So to travel with speed a greater than 1, you need empty space as well as increase your speed to go faster. You have to exert some speed. And so there are two reasons you need. So you need empty space. But the particles are moving to the right. As they move, their tail will leave some empty space. So you're also creating empty space in the motion, which is helpful for you. So you have to sort of work out how much help does it give and what is the right combination of empty space and speed that gives you the optimal rate, and how that optimal rate matches with the bound that you got before, so that you can say this fully explains the reason how the large deviation happened. So what you need to do is create an initial profile. There's room in front that starts from 0, stays flat for a while, and then rises to, that's best explained by drawing a picture. So here is rho. You're starting, initially you have a region for 0, and then you raise to the level rho again. So this is sort of the profile you start with initially. And then this whole thing moves, and this point moves, and this eventually catches up with it until you reach a profile like this, and that's what you have at time 1. So the movement of the profile can be tracked. So the rise, the way it turns is the angle at which it rises sort of twists around and becomes vertical. And that's how the, so you can write down what the initial profile is, and the rate is to be speeded up from 1 to a, and they all have entropy cause. You can compute the entropy of changing the initial profile and changing the speed, add the two entropy, it'll meet, it's exactly equal to the large deviation rate you had before. When A is between 1 minus rho and 1, the tap particle doesn't have to speed up, it can travel at its own speed, which is rate 1. If there is empty space, just create enough empty space so that it can move freely, and that would be it. When A is less than 1 minus rho, the tap particle has to be slowed down, and there are two ways of slowing down. The usual particle itself, which has jump rate of 1, can decide not to jump. Or maybe by chance you had more particles in front of the particle so that its speed is curtailed. So any combination could be the reason for it. And you can work out which is good and which is expensive, which is inexpensive. It depends on the value of rho. If rho is nearly 1, it doesn't cost much to fill it up. But if rho is very small, then to make it come up to nearly 1 is very expensive. So the entropy cost will depend on rho, and that will decide which is really the one that's effective here. So that's how you figure out what are the causes of these large deviations. So the case when rho is small and rho is nearly 1 are definitely to be treated differently. The situation for ASEP is quite different. There is no formula for the distribution of xt. Whereas for TASEP, we said the distribution was Poisson. Here you don't have a formula for the distribution. And there is no formula for the rate function either. There is no guess as to what the rate function is. But by subadditivity, one can prove that the generating function, the exponential moment, the log divided by t, as a limit exists, and this is a starting point for many large deviation results, because you can use Chebyshev Markov inequality on the expectation, and you get exponential bounds, and you optimize with respect to lambda, you get the best possible exponential bound. And this usually works out very well. But the one disadvantage here is that you don't have an explicit formula. You just have something that says...
Recording in progress.
What did I do? I pressed something I shouldn't have pressed.
I'll just close.
It's the next talk. I'm not going to give that talk. Okay. Okay, thank you. Oh, I've been clumsy, sorry. Okay. The subadditivity. Oh.
Yeah.
The procedure outlined for TASEP lower bounds will work. Constructing the lower bound doesn't care whether it's TASEP or ASEP, which is the computation is different. But what you can't say is the estimate you get from ASEP, the best possible bound you get, is really the correct bound. It's just one side of it, and you need to check the other side to match it. Now the ASEP has a speed, which is p minus q, which is 2 rho, which is 2p minus 1, call it gamma. So that's the speed at which you expect it to go if there are no particles in front. If there are particles in front, this has to be multiplied by the density of the particles, which is 1 minus rho, to catch up. So what we have for TASEP as well as ASEP are estimates and the rate functions at the upper tail. So these large deviation estimates we get are for probability that xt is bigger than something. So this is the upper tail of the distribution of xt that we are estimating. Now, upper bound for the rate function is the same as the lower bound for the probabilities, because the probability is e to the minus the rate function. Now, this function a log c minus p c minus q over c plus 1 is will play a role. What it is, you see, the ASEP process can go left or right. So if you wanted to I did something wrong?
No, some technical problem. In the lower right corner.
There's a small box. That's where.
Can you see it? Oh, this.
Oh, okay, thank you. So one way the attack particle can move faster in ASEP is either it can increase the rate for going right or decrease the rate for going left. Both of them are expensive, but to achieve the same result, how do you balance the two? What combination is the best thing? That's what C is the ratio between the, and that'll come up. So C is computed to be the optimal way of doing it is P is pushed up to PC and Q is pushed down to Q over C, and C is this combination. Now, one way of thinking about it is, after all, the tag particle has no will of its own. I mean, it can move one step to the right or one step to the left, and then it bumps into other traffic. So the entire flow of the tag particle is determined by the flow of the traffic as a whole. So the whole system has a certain motion, and the tag particle's position is completely determined. But the flow is completely determined by the initial condition, because this is simple exclusion, and the shape evolves like in Berger's equation, and so you know how what the flow is. So in some sense, if you know the initial situation, you know exactly what the tag particle will do. So you can optimize the initial condition or all possible flows so that the tag particle is where it is. That is one way of directly computing the large deviation probabilities of the tag particle. So our best possible lower bound that we can have for the tag particle to move A, balancing the entropy cost of removing some particles, speeding up to the right, and slowing down to the left. All these things you can do and optimize. And the best possible bond you can get is this: A log C minus PC minus 1 minus rho over C minus A log 1 minus rho minus gamma rho, where C is we expressed before the ratio. Yeah. And that's for A bigger than gamma. If A is smaller than gamma, then you need slightly, you don't have to worry about going to the left. You go to the, because you don't want to go very fast. You want to slow down, then you go left. at the usual rate. So anyway, these are the best possible bounds one can get. So we will have match them with the upper bounds, the other side, to get a large deviation probability. And you get two possible variational problems here. Now, here what's happening is, now the flow, when you modify the flow, the modified flow will still satisfy Berger's equation. That's because it's known that the probability of the flow not satisfying Berger's equation is super exponentially small. Since we are interested in the exponential rate of probabilities, you can't have anything other than weak solutions of Berger's equation. Now, there is a classical solution, which is the entropic solution, which is given by Lax formula, which is variation formula for it. And any other flow which is not the entropic flow necessarily has a smaller flow than the entropic flow. The entropic flow is the dominant of all other possible things. So you can, what you're doing here, you're minimizing the entropy for all possible flows that satisfy the conditions. And any admissible flow should satisfy this, but this may have other things too. So you're including some extra cases maybe, but that will only make the bound smaller. So the one minimization is when A is bigger than gamma, the other A is lower than gamma. And the Lax solution is a variation formula involving the convex conjugate of the function gamma times rho 1 minus rho, and that's the function g. And so what this says is you are minimizing over all possible flows that can happen. These are weak solutions of Berger's equation. Any solution has to be a weak solution, as I just now said. Weak solutions have smaller flow compared to entropic solution. It's given by Lax formula. The flow for anything we construct has to have smaller flow. So we minimize over a larger class. They have unique minimizers, which are V1, V2. They can be explicitly solved. And when you solve it, they match the rate function exactly. So by doing the optimization problem, you can get the exact rate. So in this context, the following general variational problem arises. You have a convex function that's strictly increasing in interval AB. And you minimize this KABV subject to VA equal to 0 and VU is less than or equal to H of U on AB. So the problems we handled were this type of variation problems. So you can solve this problem exactly by usual classical calculus of variation methods, and you get explicit solutions with explicit bounds, and the convexity conditions ensure that the minimum is unique, the minimizer is unique, and exact calculations match with the other rate function. So the rate function you have is for A greater than gamma, the limit sub is less than or equal to minus, I'm missing. And here you don't have the optimization with respect to the jump to the left. So it's a slightly different variation problem. They match the lower bounds. Thank you. Still plenty of time, but there have been talks that went beyond half an hour. I always find that whenever I do slides, it just goes so fast. You can ask.
Oh, there is time for questions. No questions? So I seem to have read at one time that one of these bounds goes as the t squared and one of them goes as t cubed in one direction, in the other direction. Is that it's roughly kind of true?
So there's a different
The,
kind of problem.
the bounds in for more velocity are different than for less velocity in time.
That depends on some processes are very highly correlated. And that doesn't happen so much for Poisson type independent things.
Okay. Okay. Yes, sir.
So can you formulate these results in terms of conditional probabilities, like given that the particle has moved a certain amount, the conditional probability of some event will be high?
Yes, because so long as the minimizer is unique, you look at the solution with the minimizer. And if you have any solution which is not that, the probability is exponentially smaller. And that's just a consequence of loss deviation.
Yeah. So in this case, what would such a statement be, for example, if you want to formulate it in terms of a conditional probability statement?
If xt moved to a certain point, say A is bigger than 1, and you know that the initial profile had some gap in it, and it had a rise exactly like this, and it speeded up to rate 1. So all these things that produce the lower bound must have occurred. So it explains that in log deviation, one of the things is, what is the minimizer? Once you know what the minimizer is, then if it's unique, you can answer all these questions. What do you see? What other rare events occur along with this?
Other questions? Yes. Excuse me.
For finding lower bounds for these large deviation events, we make constructive proofs. So I was just curious, like in the ASEP process, what kind of initial condition leads to like high velocity profiles, like the event of high velocity happening? Like what kind of initial conditions? Like it's intuitive that to the
it's a
right.
combination. It's a combination of initial condition.
Yeah, but do we know like how exactly do they look like?
Yes, exactly.
We know them
that.
exactly.
We know that because we know the minimizer.
Yeah.
Once you know the minimizer, you know the shape of the initial curve, and also how much is the dynamics affected. Did we increase the rate for the jump to the right? Did we decrease the rate for jump to the left? All these things are worked out.
Yeah, I was just curious, like how the initial condition looks like.
I think the answer is that some of the initial conditions are that there are fewer particles to the right, then it can go fast, or the density was the same, but the thing jumped faster.
Yeah, I was like thinking like how exactly does
You want to know the exact shape?
Okay, we will discuss later. But, okay, other questions? If there are no other questions, we thank the speakers.